Welcome back. This is week 13, and in this week we're going to be looking at estimating a population proportion. To do this, we will use a sample proportion to estimate the population proportion with a confidence interval. The requirements for using a normal distribution as an approximation for a binomial distribution are the following. The sample must be a simple random sample, and the conditions for a binomial distribution are satisfied. That is, when we talk about the conditions for a binomial distribution, are that there must be a fixed number of trials, n trials. There are only two possible outcomes, success or failure, and the probability of success, P, is fixed, and the probability for failure, Q, is also fixed. Also, NP, which is the number of trials times the probability of success, must be greater than or equal to 5, and NQ, which is the number of trials times the probability of failure, must also be greater than or equal to 5. When P, the probability for success, and Q, the probability for failure, are unknown for a population, we use the sample proportions to estimate the values of P and Q. Here, we're going to need some new notation, and so P is going to represent, let me actually make this font a little thicker here. All right, let me fix that up. Okay, so P will represent the population proportion. So we're going to say P represents, I'll just abbreviate population, our population proportion. And that could be any proportion. Maybe it's the number of females versus males. So something that describes the population. P hat, and this is when we put a little hat above it, that represents the sample proportion. That is our sample, rather than the population, proportion. And when we're talking about the sample proportion, generally the sample proportion is actually equal to our number of successes over the total number in the sample size. And Q hat, that is equal to 1 minus P hat, and that is the sample proportion of failures, okay? So that we say this is our sample proportion of failures. Let me back out of that. Erase that. There we go. That's a T. Portion of failures. So here we have, this is our new notation. P, population proportion, P hat, sample proportion, Q hat, that is the sample proportion for failures. So here we're going to look at some definitions. And our first definition is what we call a point estimate. It is a single value used to estimate a population parameter. And for the variable we use for that is a P with a hat over it. And that is our point estimate. The next is a confidence interval. And a confidence interval is a range of values used to estimate the true value of the population parameter. So when we're talking about a confidence interval, we usually refer to CI for our confidence interval. Now, the next is that the confidence level is the probability that a probability that is the proportion of times that the confidence interval contains the population parameter. So when we're talking about a confidence level, it's actually it is 1 minus alpha, and it is a probability. 1 is 100%, and we subtract alpha, where alpha is the area to the left and the right of our normal distribution. Let me draw a graph down here, and I want you to imagine this is a normal distribution. So here's our normal distribution. So when we're talking about a confidence level, we're talking about if this is the center of our normal distribution where our z-score is 0, we're talking about the area to the left and to the right of 0, which is 100%, 1 minus alpha, and alpha, it would be these areas here, the area to the left of that line, to the right of that line and to the left. In other words, this area to the right of the line is alpha over 2, 1/2 alpha, and this area is also 1/2 alpha. So this area right here to the right of that vertical line that I drew, and this area here to the left of the vertical line, those areas are each half of alpha, and when you add them up we get a full alpha. So the area under the curve that I didn't shade, that is the area that's here in the middle, is 1 minus alpha, or 100% minus alpha, which would be these two areas here. Now, moving forward, the last definition is what we call a critical value. A critical value is a z-score that separates the sample statistics that are likely to occur from those that are unlikely to occur. And what we use for the critical value, we're talking about critical value, and let me go back to blue, I was using blue. Our critical, oops, move that up a little bit there. Oh, I should not have done that. Let me fix this. I cut off some of the writing. I didn't want to do that. There, okay. When we're talking about a critical value, that is a z-score, and we write this as a z with a subscript, and the subscript is alpha over 2. Now, if we look here where this line is, and this line, these are the lines that separate the middle area from the two alpha areas. The z-score for that line is our critical z-score, critical value. So this is z alpha over 2, and this is also z alpha over 2. Those are our critical values. There's one to the right and one to the left. All right, let's look at finding the critical value, the critical values for a confidence level of 95%. So our critical values are z-scores. So to create a visual, here I'm going to draw a normal distribution. This is just, imagine this is a normal curve. And here's my vertical line where I have a z-score of 0. And what I want to do is I want to find the two critical values, or z-scores, to the right and left. That is my z alpha over 2, sub alpha over 2 here, and I have another z sub alpha over 2 here. And I want to find out what are these scores. And the one to the left is negative, the one to the right is positive. What will they be equal to? So what I'm doing here is, let me change my color up a little bit. Let's say I care about this area And let me back out. Let me make this area blue. So this is, I care about this area here and this area here, the blue areas, okay. So these blue areas, let me go back to it. I'm going to change my font, make it a little smaller now. Okay, these areas that we're talking about, where to the left is my area alpha over 2. That's 1/2 of my alpha area. And this is the other half of my alpha area, so it's alpha divided by 2. And that area would be what's left after we take out 95%, because in fact, the 95% confidence interval means that 95% of the area under the curve will exist from our left critical value to our right critical value. So this area that is not shaded is 95% of the area underneath the curve. Okay, so that means if that when we talk about 95%, that's the same as 0.95, and if 100% is 1.00, we have to say if we take 1 and we subtract 95%, we're going to get 0.05. That's what's left over. So that's what alpha is. But if we want to know what is alpha over 2, we have to cut 0.05 in half. And if we cut 0.05 in half, it's 0.025. And that represents half of alpha. And that's what we care about here, is our half of alpha. And so what we want to do is we want to, when we're finding our confidence level at 95%, we're going to use our calculator. And our calculator finds the area from the left all the way over to some point on the right. So our calculator is actually going to find the area, the z-score for an area from the left all the way over to the right. And so we have for some z-score, or if we're looking for the z-score, you give it the area. So we are going to input the area in, and I'm going to change my font up here, use a different color. I'm going to use my calculator, and when I get to the calculator, and this is explained on how to do this in week 8. If you go back to the video in week 8, I talk about using the calculator to find z-score or area. And so we're going to use the TI-83 or 84 or 89 calculator. I happen to have a TI-83. And so if I press the second button and then the var button, I'm going to get a list. So I press second var, and I just turn my calculator off. I'm going to get a list when I press second var, and I want to select number 2, selection number 2, which is INVNORM. Looks like this, and I give it input. Now the input I'm going to give it is the percentage. So what I want to do is I'm going to give it a percentage, and the percentage I want is I'm looking for this z-score for a 95 percentile. Well, I'm not going to put a 95% here because I'm going to go from the left all the way up to this right point, where 95% is this area in between. Okay, the remaining 5% are in the tails, the left tail and the right tail. But I want the z-score here. So I'm going to have to take 95% and subtract half of alpha, 1 tail, okay? Which is why I took half of alpha. So if I take 95%, and I'll do that over here, I'll do it in red. If I take 0.95, and actually I'm going to have to add half of alpha, 0.025, and I end up with 0.975. Okay, so 0.975 is this 95% area plus the left tail. This left tail is 0.025, half of alpha, right? Matter of fact, if I write that in, that might explain it a little bit better. That 1/2 of alpha is 0.025, and also over here, this half of alpha is also, if I can squeeze this in, 0.025. My calculator when it wants to find this critical z-score right here, I have to go from the left and take all the area from the left all the way over till I get to my z-score, which means I have to take my 0.025 area and my 0.95 area and add them together, which is what I did down here, which gave me the 0.975. So this entire area here is 0.975. And of course, if I added this last tail, I'd have 100%. But we just want it here. So in my calculator, I'm going to enter in 0.975, and then I have to close it. So let me go ahead and do that right now. Enter in 0.975, close it, press enter, and the calculator is going to give me back my z-score, which is 0.1960. Okay, that's the z-score. That's the z-score that is z alpha over 2, which is my critical value. That is the critical value that I'm looking for a 95% confidence level. So this z-score, or critical value, is 1.960, and the z-score to the left is negative. It's the same absolute value, but it's negative 1.960. So this is how we find our critical values. Here we go. Our critical values for a certain confidence interval using the calculator. When data from a sample, a simple random sample, are used to estimate a population parameter, and P is our population parameter, the margin of error, E, is the maximum likely difference between the observed sample proportion, P hat, and the true population proportion. Okay, so to find E, which is our margin of error, it is equal to our critical value, which is a z-score, z sub alpha over 2, multiplied by the standard deviation. So I could say that's multiplied by S, which is the standard deviation. But I'm not going to use S because we are actually talking about using a binomial distribution to represent, a normal distribution to approximate a binomial distribution. So we're going to use the formula for standard deviation, and that is the square root of P hat times Q hat over N, where P hat and Q hat are our samples probability of success and probability of failure. That's Q hat. P hat, which basically P hat is, let's think about what P hat is. P hat, if we come down here, of course that's for our sample's probability of success for what we want success to be. Now, success, for example, could be how many females, okay? And that would be denoted by X. And so there are X females in the sample of a sample size N. So P hat, which we have right here, is merely the number of females divided by the total sample size. And then Q hat, of course, that would be the number of males, but an easy way to find Q hat is 1 minus P hat. So we can find P hat fairly easily and Q hat fairly easily if we know what X is and our sample size. And of course the last bit of information for this calculation we need is N, and that's our sample size. And so that's going to give us our N, our P hat, and our Q hat. And of course we need to know our critical value, and the critical value all depends upon what you want for a confidence interval. because you've got to go find that, and you can use your calculator to find it depending on if you want a 90% or an 85% or 95% confidence intervals is fairly common. So that's how we find our margin of error. This is the formula right here. Okay, here we're going to look at how to find a confidence interval for the population proportion P. And we're going to be using a sample proportion. So we're going to have a sample of size n. So the size of our sample is n. And we're looking at some proportion. Again, we'll assume our proportion is the number of females. So our number of females could be their x, let's say, females, for example. And it doesn't have to be that, but I'm doing something that's a binomial, which is either male or female, so x females. And so I know that for my sample, my p hat, which is my sample proportion of successes, is x over n. And my sample proportion for failures, which is q hat, is 1 minus p hat. And so if I want to know my my estimation of error, well, that's going to be my critical value, z alpha over 2, which we looked at finding that using a calculator if we know what we want for a confidence level, times the standard deviation, which is the square root of the p hat that we just found, times the q hat divided by n. Now, of course, I have to know my confidence level. Let's just say that my confidence level, we can use the confidence level we found earlier with the calculator, which was confidence level of a 95%. And so if we know that that's the confidence level, then we have our critical value z-score, which was the 1.96. Okay. Okay, so what we want to know is we're actually looking for the confidence interval, so it's an interval. And it is the interval where we would expect P, which is our population proportion, to exist, okay? So we're saying that the value of P should be some value between our samples proportion, so the population proportion should be some value between, I should maybe start from left, our sample proportion minus our estimated error, and our sample proportion plus our estimated error. That is to say, imagine we have, think of this as a number line, and this is our p hat value. This is some value. This is our samples proportion of maybe the sample proportion is some x over the total number in the sample. Okay, that the actual population proportion would exist somewhere in the interval between p hat minus our error estimation or margin of error, and p hat plus our margin of error. And that is to say that somewhere in here is where we would expect to find the actual population proportion, P. Now I want to add to this saying that we can certainly write, this is one way to write our confidence interval, but the confidence interval can also be written as p hat, that is the sample proportion, plus or minus our margin of error. That's another way to write it. Or we could put it in parentheses and say, this is interval notation, from p hat minus our margin of error to p hat plus our margin of error. So I've just given you 3 ways to write this. We can write it as an inequality like this. We can write it in interval notation, and an inequality is actually mathematically, this is set notation, or we can write it in interval notation, or we can just say p hat plus or minus our margin of error. And that is our confidence interval. Okay, now here we're going to look at constructing a confidence interval. What are the steps? Keep in mind that when you are finding your confidence interval, you want to round it to 3 significant digits. I put that in red to help you remember that. Okay, so the first thing we want to do is we want to verify that the required assumptions are satisfied for approximating a binomial distribution with a normal distribution, and we went over that earlier in the video. And the next thing that we want to do is select a confidence level and find the corresponding z-score or critical value for that confidence level. So we're going to decide that what is our confidence level going to be. And well, we can say maybe we've decided it's going to be a 95% confidence level. And so if we know that that's what we want for confidence, and it doesn't have to be 95%, it could be anything, we then want to find our critical value, which is z sub alpha over 2, and we went over how to do that with the calculator. And when we did that with the calculator, we found that the critical score was 1.960. Okay. And the next thing we want to do is calculate the margin of error using the sample proportions. Okay, so let's go ahead and let's calculate our margin of error. And so we're going to say, well, I have my sample proportions. I have p hat, I have q hat. These are my sample proportions, and I have n, the sample size. So my margin of error, E, is going to equal my critical value, z sub alpha over 2, times the square root of p hat times q hat over n. And we can put that into our calculator. And the next thing we want to do is we say, okay, well, I know what p hat is, okay? And so my fourth step, and I didn't type that one up, but I can handwrite that in. Our fourth step would be to determine the interval of the confidence interval. Okay, so now we're going to find the confidence interval. And that's what we're trying to do here. And the confidence interval is going to be p hat, whatever p hat is, and that's from our sample, plus or minus our margin of error. That's our confidence interval. And keep in mind that when doing this, we have to round the confidence interval to 3 significant digits. That's 3 digits after the decimal point.